Well, good evening, everyone. It's a great pleasure to welcome you all here tonight for the next installment of the public lectures from the Kavli Institute of Particle Astrophysics and Cosmology here at Stanford, or KIPAC for short. My name's Dan Wilkins, and on behalf of myself and our Outreach and Engagement Manager, Zinan Du, it is a great pleasure to welcome you here and to see so many of you joining us both in person and online as well. First order of business, if I can please ask our in-person audience to check that your phones are on silent. And I'd like to thank you all for your interest in our lecture series about JWST. I can tell you for many of us in the astronomical community, it has felt like an extremely long time coming. But it is really exciting to be able to see some of the first data from this spectacular new space telescope. And we had our first lecture about that last month when Dr. Ren Soos was talking about how JWST is already helping us better understand the most distant galaxies. And we continue in that theme tonight, where Dr. Simon Birrer will be discussing how JWST can tell us about the nature of dark matter and of dark energy. But before I introduce tonight's speaker, I'd like to give a big shout out to the entire team working behind the scenes. We have our technical team here tonight who are working on the cameras and the audio to make sure that you can see and hear us. And for those of you on YouTube, we have some chat moderators joining you who are experts in this subject and will be able to help answer some of your questions as you post them in the chat. So I'd like to invite our chat moderators to introduce themselves. Ren?
Hi, everyone. I'm Ren Soos. I'm a joint fellow at KIPAC and UC Santa Cruz. I study the formation and evolution of distant galaxies using JWST. I gave the last lecture, so I'm very excited to hear about cosmology tonight from Simon.
Thank you. And Jelle?
Hey all, I'm Jelle. I'm a colleague of Simon, also a postdoc at Stanford, and I work on trying to find dark matter with telescopes in space and deep underground.
Excellent. And Sandy?
Hi, everyone. I'm a research fellow here. I work on large-scale structure, the cosmic structure of the universe and galaxy evolution using large simulations.
Excellent. Well, thank you so much. And for those of you on YouTube, we welcome you to engage in tonight's talk via the chat window on the right-hand side of your screen. In that chat window, you can post any questions you might have about what you hear tonight, or start a discussion with some of your fellow viewers, though we do please ask that you be respectful to others. And our expert chat moderators here will be able to help answer some of your questions as they come up. But those of you in the room, fear not, you will have an opportunity to ask questions as well. After the talk concludes, we will have a live Q&A with Simon up on the stage when we'll be able to put some of your questions and some of the questions from the online audience straight to him. So without further ado, let me introduce tonight's speaker, Dr. Simon Birrer. Now, Simon is a Kavli postdoctoral fellow here at KIPAC, and his research is all about probing the fundamental physics of our universe on the largest cosmological scales, in particular using the phenomenon of gravitational lensing, looking at how material in our universe, in particular the structure of dark matter in our universe, bends light as that light travels towards us. Simon is involved actually in several JWST programs, so we're really delighted to have him here tonight to tell you firsthand all about the amazing new science that he's been doing. He received his PhD and his undergraduate education from ETH in Zurich, Switzerland. And before coming to Stanford, he was a postdoctoral scholar at the University of California, Los Angeles. And I'm sorry to say that Simon's actually going to be leaving us very shortly. He's moving to a new position as an assistant professor at Stony Brook University in New York. But it's a real pleasure that we could get him to speak to you tonight before he leaves. So without further ado, Simon, take it away.
Thank you so much. Oh, wonderful. Wonderful. It's a great pleasure to be here. Welcome, everyone. Today, I would like to talk about the history of the universe, what it's made of, and most importantly, what we don't know of it. And I can already tell you, it's a lot that we don't know. And that's why, in particular, we are so excited to having a new tool in space, the JWST, that we hope that it helps us, guide us to a better understanding of the history of the universe and our place in the universe. This talk is titled Shedding Light on Dark Matter and Dark Energy, two phrases you may or may not have heard, used as buzzwords floating around. In short, they stand for I don't know and I don't know. But during this talks, I go through what we actually know about it, where we stand right now, why we are struggling, and I'm going to showcase a few experiments we are conducting with the JWST that helps us further guide in a direction of our understanding. We're getting a bit of sound echo. The reason I can stay here in front of you and be semi-confident talking about our universe is not because we have great thoughts necessary about the universe, but it's because there are decades-long tedious experiments that we measured and mapped out the universe that helped us guide of where we are in the universe. And that's why I can give this lecture here telling us, or I'm certainly not fully convinced of what I'm saying is true, but I have a good background and story to tell you from that data. So cosmology, this is what it is, a physics discipline, an empirical disciplines about the largest scales about the universe. It's not about our planets, it's not about our solar system, it's about what galaxies do, how the largest scales in the universe that we can span and can see and visualize. That is cosmology. And this is a data-driven subject. And what you see here is a set of images from data that we've collected over the last few decades that spans from galaxy rotation curves of individual galaxies to the dynamics of clusters of several hundreds of galaxies, how they interact and how they flow through each other, to how clusters collide and what the gas is doing, for example. But then we can go even further out and take a bigger picture, say like, how do galaxies cluster in the universe? And we see here like kind of like a spider web of galaxies, how they are clumped, how granular the structure we find to see in the universe. Two, and this is what I'm going to talk a bit later, light is being bent, and we can see this shearing and distortion effects in the universe on the very largest scales. And we can map the matter distribution of the universe over a large scales and epochs. And last but not least, the cosmic microwave background, the afterglow of the Big Bang, the radiation of a hot plasma that has been emitted billions of years ago, that reaches us now, rather called as a background noise. And all these observations together, and even more that I'm going to show, leads us to a rather consistent picture of how we think the universe has evolved through cosmic time. And what I show you here is not the pretty picture of or visualization of the data, but is actually what we compare of that data with our models. And so just as an example here, this is the cosmic microwave background in a space that is not really important, but the data points here describes the statistics of the patterns that we see imprinted. And this line going through the middle is a model. And so we have at least one model that describes that data remarkably well. And so for other observations of how galaxy clusters, and here a line through is a model. How the universe expands, I come to that later, and the black line through it, and this is a model. And it's always the same model that describes all this data together. And this is a remarkable success of cosmology, that we have the ability to describe the data. So we have at least one model that is excellent in describing this data that we have collected. That doesn't mean this is the correct one, but we at least have come to the point where we have such a model. And what does this model entail? And here the struggle starts. The first, and this is, I feel, the most fundamental, but it's often forgotten a bit, is the Copernicus principle. There is no special place in the universe, whether it's here on Earth, or solar system, our Milky Way, nor everywhere. So wherever we look and wherever we see things happening, they're self-similar. There's nothing more important why we are here or somewhere else in the universe. That's the Copernicus principle. And I put here also that this comes from 16th, 17th century. The second pillar is general relativity, our current theory of gravity, how gravity works in a universe on the largest to very small scales as we stand here and getting hold on the ground. The third pillar, not so much a surprise, the standard model of particle physics. That's what we are made of. This has been effectively completed to that level and in about the 1970s to the stand we are now. And so, and this is how particles, how the stars shine, is very well described within this model. So we wish we were complete with these pillars, but no, there's this thing that we call dark matter, which dominates the entire matter budget in the universe. First sign came around in the 30s, and it got more and more accepted around the 1980s, when the term may have appeared more frequently in textbooks, let's speak that way. And then last but not least, dark energy, which is a placeholder that describes the accelerated expansion in the universe, and only detailed observations in the 90s have indicated, in the really early 2000s, Cell nailed it, we need these additional components to it. And the reason I talk about dark matter and dark energy is not because it's some fancy terms, it's actually we need something to describe this wealth of data. And when we now look at the composition of the universe, we can make a pie chart, and this is what currently we think. Our best guess what the universe is made of right now is this 4.9 or 5-ish% is the ordinary matter that we know, that are described by the standard model of particle physics. Here, what we are all made of. About 5 times more is in the form of what we call dark matter, which is unknown, it's transparent, we don't see it, we don't taste it, we don't smell it, but we know it interacts gravitationally to make up the universe, as to be able to describe the universe as we see it. And then this very large component is what we call dark energy, which is responsible for the accelerated expansion of the universe, a negative pressure that pulls objects or galaxies away from each other, and over the long terms leads to an accelerated expansion of the universe. And so if I look on this, still after years, almost a decade that I'm in this field, since I started my PhD, I still think like that. That thing I know, I'm kind of like familiar, and some people even know it better, the particle physics, that people are working on solid state physics, etc. Then dark matter, crazy, no idea. Well, there are some ideas, and I value all these ideas, and some are actually quite nice ideas, but we don't really know whether they are the right ideas. And then dark energy, accelerating expansion, who had thought before we measured it? We measured it, it's there. How do we deal with it? I don't know. Also, there are good ideas around of what this may or may not be, but which one is the right one? We don't know. And before going now a bit deeper into that dark matter and dark energy story, this seemingly small part is actually what we can see in the universe right now. The galaxies and every data that I showed you effectively relied on something that we see and observe. And I would like to highlight here the talk by Dr. Ren Sis, who gave the first public lecture in the JWST series about the distant galaxies, where she describes what this portion is made of. These beautiful galaxies are made of. And she also lays out a bit the story and the history about the JWST, how it's being built, launched, and what amazing capabilities they have. So I invite you very much, go and watch it. If you're on YouTube, you see on the same channel this lecture being present there. And without further ado, let me dive a bit into the first part of dark matter. Even though we don't know what it is, we can hypothesize what it is, and we can run it in a computer to see what will it predict, what structure emerge, what is going to happen. And we can put this in our computers. And what happens is that over time, when we let gravity do its thing, GR basically, we see such structure emerge of a collapsed structure bound together that is slightly fragmented. So gravity is a attractive force, and so where there's more matter, it attracts even more, and it leads to something like a collapse of structure together, what we call a halo. What we don't know is, but here we can either say dark matter is of this kind of weakly interactive massive particle, which is here on my right, or weakly interactive, but not so massive particle that damps a bit the structure on the smallest scale. So we let it first like rinse away like water before we let these little waves grow back and gravity pulls things together. So there are two hypotheses. Likely none of them is exactly the truth, but there are two models that we have. What we know exists is in the very center of this collapsed dark matter structure resides the galaxies, resides a Milky Way, resides the galaxy that we see in the very early universe, and basically every galaxy we see around us. And we need this massive dark matter structure around it such that even galaxy can form. We need this potential way of attracting force such that gas can cool down within there and form the stars. So without dark matter, no galaxies. It sounds counterintuitive, but in that sense, it's required to form the structure we see. So can be in both of these scenarios as an example. What we also know, and this is interesting, these models have been around since like the early 2000s. By then, we haven't seen very small galaxies. But we predict that there is a lot of clumps here, or potentially a lot of clumps around us. And indeed, then in the early 2000s, with surveys that monitor diligently the skies, we discovered these ultra faint, we call them dwarf galaxy, so companion galaxies around our Milky Way. And we know they reside into some matter structure that is dark, so dark matter. And so we can assign these little galaxies to this small structure residing around the bigger ones. And this is a remarkable prediction that's being made before we actually saw and searched systematically for these very faint, very tediously to find, very good, well hidden in the sky objects. So they match for both. But then we start counting here. It's like, well, what this dark matter model predicts is very small clumps that are depleted of stars. There's nothing in there except dark matter, or nothing that we can see by eye that stars would shine. And this is a fundamental prediction of our current model of cosmology, where I show you the nice lines going through there, which we don't know whether it's true, but we have predictions of what may be out there, but we don't know whether or not it's being present. And this leads me now to the James Webb Space Telescope. And this is the first picture that has been released by NASA. It's not the first picture that's been taken by that amazing telescope, but the first picture that's been released. And what you see, or first question, what do you see here? Shout it out if you're in the audience. Galaxies, stars, gravitational lensing, arcs, many things. And if you're in chat, put it in what you see. And there's a lot going on. This is, I could stare, or I stare of it too long, I think, but that's also what drives to some degree my excitement for this field are such images, but they have so much information in there. And what, just to give you a little glance here, what you see here, this light yellow blob is a massive galaxy that is about 100 times more massive than our Milky Way. It is in the center of a massive cluster assemble of other galaxies that are in yellow. And these form one of the most matter accumulating objects, so to speak, in the universe. And when there is matter, mass, gravity bends light. And so if there's something behind it, it gets bent around, and we call it a lens, as if you have lenses, or you can take a wine glass and use it as a lens, a glass, a refractor, and it bends around objects behind. And these are these highly distorted images. And we knew of them, so that was not a new surprise from JWST. But JWST is so deep and so precise. And when I personally looked in this image the first time, I thought, like, you may or may not see these little stripes here and there everywhere. They were not visible before JWST. And when I saw it on the screen, I thought, like, my screen is dirty. And I washed it, and yes, it was dirty, but this was still there. And it just showcased how much information is in the universe to be extracted if we come with a telescope, an instrument that can really take this information to us. And JWST is such an amazing instrument that can do. Speaking of gravitational lensing, here a small animation of a galaxy that emits lights in different directions. And it, on the way to us or through the universe, it gets bent around. And then depending on when we're aligned on the sight line that something big and massive is in between, we see it so highly distorted. And this object here we call an Einstein ring. So when you see multiple images of the same sources as a ring form when the matter is more or less spherical being bent to us. And this phenomena can be used to study dark matter. No matter what the matter is, it bends light, no matter whether it's in stars, in gas, or in some spurious dark matter, whatever. It bends light, and so we can reconstruct and know where it is, how much it is, how granular, how clumpy it is. And that's what the one aspect of what the James Webb Space Telescope is going to do. So here, an example from the Hubble Space Telescope of such a phenomena of arc, some massive galaxy that does most of the lensing. And what you see here is this little companion galaxy that does a secondary bending here. And you see, even if you black out and if this thing was be completely dark, no stars, we would still, by just looking at what it does to the background, could pretty confidently say how much matter should be here that makes this distortion. And that game, as we see here, this is very massive, we play further down in the range of mass, further down in how much it distorts, down to a pixel, down to 1/10 of a pixel, or even below, and see whether these small scale distortions are present. And that's one project I'm involved with JWST that I'm particularly excited about. And the way we do it in brief, so here, these are quadruply imaged quasars. So 4 images of the same source, and that source is an accreting supermassive black hole. And as if this would be fancy enough, these 4 images provide us with we have an expectation of how the brightness between these images are, depending through what lensing they come to us. So we see one flux a bit more and the other image a bit less. And while this light is traveling to us, it may intervene with a lot of potentially dark structure along the way. And depending on how many, depending on where they are and how cuspy or cory or fluffy they are, it exhibits a difference in the brightness. And the James Webb Space Telescope can measure these fluxes to an incredible precise level that we cannot achieve before. And we are able to measure very small scale distortion of these flux ratios. And we can do the statistics and tell us what type of dark matter is consistent and what type of dark matter is not consistent with the observations we have. And here, this first data arrived a month ago. We're very excited, and more observation within the next few months. And we all have to learn the data products, the analysis. And this takes about 1 to 2 years to just run that analysis that we have now set up before the plan before JWST was launched. And now we have a lot of work to do. So that's one of dark matter, one project that JWST is I'm personally excited about. Let's switch gears to the accelerating universe, or dark energy, the placeholder that we use to describe this phenomenon. So here, we are present day around here. And in this kinematics, the acceleration has just started. This here is a projection of how our current best model projects of what's going to happen. And if you're interested, what are the scenario of how our universe ends, I highly recommend you the public lecture that's by KIPAC. That is also on the YouTube channel of KIPAC. That goes into the details of what may or may not happen at the end of the universe. And again, here, when we looked where we got this information about how the universe really expands, we have data. And this is one of these graphs where we looked at supernovae at different distances or at different redshifts, where we called, and this is also something that Dr. Seuss talked in her lecture. The further away objects are, the universe is expanding, and with it, the photons, when they travel. And so something that's further away has, when it's being emitted, has traveled through the universe, and the photons have expanded with it. And so we see it redshifted. And what this curve briefly is a diagram of how bright these star explosions are at different redshifts of how the universe has spread. And this has led to the conclusion that the universe needs to be accelerated to explain this data. And even more and more accelerated as time comes closer to the present day, and then we can project it even more. And this was in the late 90s, so very recently. So, but now the question, okay, we have established it accelerates, we don't really know why. But the question is how much it really accelerates. And that's a harder question than we may think. It's easier to say that something accelerates, it's easier something, the dynamic part, than actually saying how much is the current acceleration rate of the universe. Very simple question, a very hard answer. And so the first, or one of the first studies that went into that to look for how fast is the universe actually expanding today is Edwin Hubble, among others. So he got a bit too much credit for that work, I would say. But here, his diagram from 1929, where he puts here on the x-axis distances in these units of parsecs. Doesn't really matter what it is, just further away, and we are here. And here, velocity. So how much recess velocity these objects go away from us. And you can put this different galaxies. These are data points or galaxies. You can put them on the plot. And what you can do is put a line through it and say the steepness of this line is this Hubble constant. That's basically it. So if something is further away, it's recessing, going faster away from us. And the question is how fast? And for the very trained eye, the units are even wrong on this graph. And the number here is like, okay, in In 1 parsec, it goes about 500 kilometers per second away. This was then. Almost 100 years later, these diagrams are now being made with supernovae. And these are quite modest. They don't write distances here. They write this thing called distance modulus. Modulo, something that we don't know or we don't have calibrated. And so the question here is really the distance anchor. Where to come the absolute distance? How far is Andromeda galaxy away? How far is the Large Magellanic Cloud away? How far is the next star? And these are not trivial, actually very hard questions. And we're still fighting with it. And if we go through the history of recent measurements of this Hubble constant, of the current expansion rate of the universe. Here, this is a graph that dates back to about the year 2000. This graph could have made back to 1929. And just the numbers here, they're around 70. And on Hubble's diagram was a number around 500, so through the roof somewhere. And you just see how things are being still struggled. And interestingly, over the last about 20 years, these measurements got ever more precise with different techniques. And some of them tend to more and more not agree with each other. And that leads to a mystery. So an example here is what is here under CMB, the cosmic microwave background, when we assume how the universe has evolved in the very early dense plasma, how plasma waves evolve. This is a relatively simple physics. If we put it into, we get an inferred answer that is around 67 right now, really small error bars. And then we have other measurements, which we call the local measurements, and I'll come to that, how they're being done. Here with C-feed variable stars, or what is known here as TRGB, tip of the red giant branch, hold for 2 minutes. They tend to be higher. And this may or may not indicate that what I told you in the very first slide, that I'm very confident to describe the universe, I may be not so confident to describe the universe, because there's some indication that something does not really match. And if this is true, that this doesn't really match, it also would imply that the story that I told you that these black lines fit through everything doesn't work that way. And so that we need at least a different component, or throw everything away and rebuild it from scratch in different ways. And so from an experimental physicist, this is exciting to probe and test ever more precise to see where do our current understanding break. And that helps us guide of where we can put our thoughts in if we're too divergent between experiments and theoretician. But hold a second. So it could be new physics, but it could also be that some of the measurements are not as precise as we think they are. And this is a term we colloquially use as systematics, which is basically mean we are overconfident in our statement. We have forgotten to include certain, or we have not ignored that we're actually making some assumptions that may not be, they may be good, but not good enough for the specific statement that we're making. And so we're always at the edge of finding new things, learning about the universe, that sometimes we're going maybe a bit over it. And so this is tedious work to go into. Are the stated uncertainties as good as they should be? So the distance ladder, so what are these measurements made of? And that leads then to the James Webb Space Telescope again. So when we measure distances, what we can do, we can very well measure time. Clocks are extremely precise. That's the thing, the state of the art. What we can also do, we can send radar signal from our Earth, bounce it on Venus, for example, and it comes back to our dish, for example, the Stanford dish here, and we can click the time, how long it takes, and we measure this distance. Remarkably precise to something like a few centimeters. We can measure the distances in the solar system with such a radar observation. What we can't do is send this radar signal to stars away, or even galaxies that we wish that's not coming back in the lifetime, and we'll not measure in the signal. It's too weak. I wish it would be that way. And so what we need to is intermediary calibrator of how we do it. And one way to do it is what's called the parallax method. We can use the fact that the Earth and everything else in our solar system is actually rotating around the sun. And if something is above us and we're moving on the left and on the right, it changes the angle on the sky. And this is the parallax method. And so when we know this distance, we can get geometry to the stars. And amazing progress have been made, for example, by the Gaia satellite. And there are a lot of very precise techniques that measure these angles very, very precisely. So that's the next step. But it's still not the next galaxy. That is not the galaxy on the other side of the universe that we barely can see far away. So we need other, more luminous sources intermediately. And so we can use different techniques, such as, for example, Cepheid variable stars, that we can measure some of them with parallax, see how bright they are. And if they're like 4 times dimmer further away, we know it's like twice as far away. So, and then go step by step out. And if we want to go very far out, we need to have something very bright. And something very bright is something that explodes, for example, like a star, a supernovae. And so we can use then the more localish supernova, where we can still see Cepheids in there, to calibrate how bright a certain intrinsic luminosity is of that supernova, and then learn about. And you see already, like, this is a long story and I abbreviated like a lot. So recent measurements, and here come through some data point that there was one of the lines that gives a very precise measurement of the Hubble constant. This is a study with the Hubble Space Telescope, went through such a thing. And this line here is a joint fit of distances throughout, a very large part of the local universe, where we, with different techniques aligned with each other. And so this involves parallax. I've mentioned that. So this is the first rung, so to speak, in this ladder. So when we walk up, the next step is the Cepheid period luminosity. So there's a star that kind of like has a frequency at how bright it is and what period it has. And if you say they're self-similar everywhere, you can calibrate and say like, okay, this was so bright, so this has to be further away. These are the Cepheid. And then the last rung is the type 1a supernova. As you may or may not see here on this plot, they're not all the same, but they have some similar relation that you can put them on the same plot and stretch them and squeeze them, and then you can use them as calibrators. So this is a way to go out to the universe where we can really measure the expansion rate very accurately. So here again, new physics or systematics when we go through this. This is a very precise measurement. A lot went in there, but there may also be some uncertainties. There's some dust in there that we haven't accounted for. Is there some crowding effects? Do we really measure the same thing that we want? Are we slightly offset in between? Do we understand what these Cepheids are? Questions over questions that hundreds of people spend their daily life, sometimes nightly life, on to make sure that this is accurate. And this is the first publication that came out that I saw from JWST about that matter. And here it's not about, oh, a new measurement, more precise, or disagreement. No, this is just to show that in the same wavelength with a different telescope, we get the same answer. And this is just the first step when you then go forward and say, like, we now use the new techniques, the new capabilities that to make sure that under the same capabilities as before, we get the same answer. And that's just showcase, that's current status right now of what the James Webb Space Telescope is doing with the Cepheid science. And a lot is in progress here. And I'm excited to see when we push to the far infrared, whether we see either some differences in this analysis or whether it actually makes it more robust and gives another pillars like, yes, it's true. What I'm more excited about personally is a different technique using stellar physics to measure cosmology. And here we're talking about the tip of the red giant branch. In very short, a star is somewhere on the main sequence that is defined by its mass and its temperature. It burns hydrogen mostly, as our sun does. And when the hydrogen fuel is used up, it contracts until it starts the helium burning. And at one point, it creates this helium flash. And this is a specific moment where we understand physically what's going on. And that leads to a certain calibrator. If we see stars right at the tip, we can know the difference in distance, for example, in how bright they are. So this is an alternative method. And here's an example, some measurements of brightnesses of stars, where you can statistically see where this tip is. And this method currently used with the Hubble Space Telescope gives some measurement in between. It could be high and discrepant. It could be in agreement with the what we call the early universe physics. We don't really know. But what JWST is doing is it collects about 125 times more volume where we can do this measurement. And if we have done all the programs, this is really the ability to settle the debate. Settling meaning either one or the other way. Do we need new physics, or is it systematically driven? And so that's very exciting for me and many others. And again, it takes time. Multiple projects are underway, but we're just in the beginning, learning the experiment and going step by step towards it. So, and in the last few minutes, it is another measurement that I'm very excited about with, again, strong gravitational lensing, measuring the Hubble constant. And here we're using the technique called time delay cosmography. So what we measure here with quadrupole lens quasar, these images, it's the same source in the background. We're not just seeing them multiple times, but the light path, the light travel time is different between the different images. And so if we can measure that relative light travel time between that image and that image, we can get a depth information of how far away these objects are. If they're closer to us, the light travel time is shorter. The further away of us, they're longer. So we get a one-step measurement of distances right away. And this is exciting. And so here, for example, these quasars flicker. And so we can adjust the flickering to each other. And we have also experts here in the audience that do that very well and very precise. And here, again, we have a precise measurement. It seems to be high. But again, extraordinary claims require extraordinary evidence. And depends on how you do it, depends on how you run the assumptions. You may or may not find the same answer. So we're really opening the box again and again and again. And there, JWST is very impressive, where we can do spatially resolved studies of such deflector galaxies where we currently have not so much knowledge about that, to really anchor down and show, are our method robust enough? And this is just the beginning of the studies. And with that, I want to conclude. I showed you a bit about dark matter, dark energy, where we are right now, the open questions. I showcased you just a few examples of what's going on right now. And conclusion here, be patient and curious. And JWST is the most complex instrument that's been flown to space, which requires us a lot to learn about that instrument before we can really trust what's going on. And that just takes time. And it works extremely well, but understanding the instrument takes just time. I'm within the 1 or 2 years, I highlighted a few studies of dark matter and dark energy that hopefully change a bit our view on this. And the legacy of JWST will be decided not in this next few months. It's an instrument that's out there for 20 years, and it's our imagination how we use it to change our perception or view of the universe. And with that, I say, thank you very much for your attention. I'm looking forward for your questions.
Wow, that was a very amazing talk. Thank you, Simon. It feels one of those talks where you've learned so much, yet there's even more questions coming up. So I'm sure there are a lot of questions from the audience. We can start to take in-person questions. So feel free to, over there.
Hi. Do we know if the universe is finite or infinite, and how does that tie into the rest of the pieces of the puzzle?
Yes.
Great, thank you. I'm gonna just quickly repeat it for our Zoom audience. So the question was, do you think the universe is finite or infinite, and how does it tie to the entire paradigm that you were just talking about?
Yes. So the Copernicus principle states that there's no place in the universe that is more preferred than other. And if you take that to the extreme, as soon as you have finite, you need somewhere boundaries. And as soon as you have a boundaries, you're somewhere in the middle of it. And so the principle that there's no special place requires you directly to not have boundaries. We don't see everywhere, so we only get light information that travels to us. And so our accessible universe is finite. Of what influences us here, the story that we were written, the history of the Earth, of our solar system, is finite of what it could interact with, but there's no border, and so in that sense it's infinite. Yeah, and that is part of the cosmological picture that is over and over confirmed by data. And regardless of where we look, we see the same thing and no boundaries.
Great. There is actually an online question from Tyler, also asking about space and the universe, of course. So are things really moving through space, or are they just appearing to be moving just because the space itself is expanding? And if the space is expanding itself, what is it expanding into?
Yeah. I must say I'm always struggling with it. The way I imagine it for me is, if you think of a grid that you lay out that never ends, you always can put in another line in your grid. Again, comes back to there's no center of that grid. And now you can say, like, you squeeze all the grid points slightly more away from each other. This means if you go the first grid point one step away, the second one needs to go 2 steps away, such that the second and the third one is also going apart from each other. And in that sense, it doesn't expand somewhere else. It's an infinite grid that just expands itself and constructs. So it's in itself that it expands.
Thank you. Over there.
Well, the honest answer is we don't know. The best answer I can give is it most likely does, as well as everywhere else.
If it does, then why do we need telescope? We can just do research over here.
It's a lot of people do that, in fact. And the problem is they haven't found anything. They build better and better detectors, and they're well designed. They measure incredibly well anything that may come and give a bit of recoil to atoms. But if it's not interacting with the thing that we can control and measure out of devices, then we don't see it. And so in that sense, it's a multi-pronged problem, or a multidisciplinary problem, dark matter. There are particle physicists that work on the ground here. There's a lot of people actually at KIPAC that design these detectors of seeing it. And what we are doing here at space, we use space itself as a laboratory to see whether we can learn through the gravitational physics, how it imprints in our cosmology, of whether we can learn something about the microphysics, we call the fundamental principle behind it.
Great. Question here.
So if we have dark matter out there, but none here, and we have the speed of light, we assume it's constant here. Is it safe to assume that the speed of light is constant over there? The data we're getting, assuming the speed of light is constant over there, represents something meaningful?
So the speed of light, this is one of the...
Can you also repeat the question, please?
Okay, so the question was whether we can assume that the speed of light is constant everywhere, when sometimes maybe dark matter is maybe over there, but not here. So experimentally, the speed of light is so well tested that actually now the definition of what length is tied to it. So we cannot change the speed of light by definition. It's effectively, it just shows that experimentalists can measure time so well and have lasers that reflect or can interferometry. That's basically locally how it's been done. The measure is so precise, and it has always been confirmed that they came to the conclusion we're actually fixing length scales to the clock. That only works for us experimentally on Earth or on our solar system. That definition we cannot use on cosmological scales. And so we have to extrapolate and rely on general relativity to give us the relationship between matter and length.
Great. Okay, so we'll take more in-person questions, don't worry. Actually, I wanted to switch gear a little bit. Also, there are questions from online asking, especially this one from Phil, asking what phenomena or factors that might actually degrade JWST accuracy over time.
And one we've already seen, there was a micrometeorite hitting the telescope, one of the mirrors, and this was not expected. Well, little objects are in space, that's expected, but how big and energetic it was, that actually almost destroyed one mirror segment. And so, and this happened very early on when they open up the telescope. And so, oh, if this happens every month, we're learning out of mirror time. Luckily, was a one-time event, fingers crossed. And so this will last. What will degrade over time is some like mirror coating. Here on Earth, we can repolish it. That doesn't happen on space. And what eventually dictates the lifetime of the telescope is the fuel. So we need external energy or energy that we send with the telescope to actually turn it, twist it, and cool it. And once the energy is run off, it cannot stabilize on that orbit where it is, and we cannot turn it anymore, and it will just go into outer space. And that's in about 20 years.
Well, we still got some time. Things are not started yet. I saw a question over there from our probably youngest member of the audience.
See what's on the seconds, like, or minutes. It's called actually years. If we look at a really far point, we will see it before basically on the minutes. Is there a way to see the Big Bang?
Wonderful question. The question was from one of our, if not the youngest audience member here in person, is if we look at the star further away, we expect the light of travel to us, so it's older. So, and the question, if you go do it all the way and say like, hey, can we see the Big Bang if we go further and further away? And if the Big Bang itself would have emitted light that travels to us, we would see it right now. At and very close to the Big Bang, the universe was so dense that light could not escape. It just bounced back and bounced back. But then at one point, the universe became less dense, expanded. And at one point, these photons did not bounce back anymore and start traveling freely. And that moment we can observe. These photons we collect. And these are known as the cosmic microwave background. It's the earliest picture of the universe we have. A few 100 million years after the Big Bang, which is a relatively short time scale. And that is the picture that leads to why we call it cosmology, why we call it a Big Bang, why we think the universe came from basically one point and expanded. Wonderful question.
Great, over there.
So yeah, thank you for the question. Why is the CMB image like so essentially like noisy? Like why does it vary so much?
It's first it has a bit of okay. The question was why the cosmic microwave background image. This was one of the first top left images. Is so noisy or wiggles so much. So first, it's not noise; it's actual signal that we see, and it's not so much. It's the artist or the person that makes the graphics that enhance the signal. So this is one part in 10,000 difference between what you saw in red and in blue. So the universe was basically the same density and temperature, but just one part in 10,000, a bit more over there than say like a degree next to each other. And the signal of these little differences are actually very crucial. So what happens there is, in the very early universe, there were some density fluctuation. We don't know exactly where they came from. We assume it's quantum fluctuations in the very early universe that dictates uncertainty of where things actually happen. And once the structure grew, they were imprinted. And then what happened is that the plasma, the very energetic particles, they travel in, or they have a sound speed, or things travel with a certain speed. And if you let this structure evolve, these wriggles, they happen to be on certain scales on the sky. When the CMB, actually we see it, the structure. And these scales of how close a black and the red dots are from each other, which is about 1 degree, is according to that prediction of how these density fluctuations evolve and go through that pressures fluid, effectively, plasma. Yeah. And so these ripples that you see there later grew into what we see as the galaxies, the cosmic web, the spider structure of these, and we can consistently trace the statistics of these fluctuations forward, and they are according to the expectation of where galaxies are around now. Without this wriggles in it, there wouldn't be any life, there wouldn't be any structure, it would just be boring, flat, helium and hydrogen, nothing else.
Great. Over there.
If dark matter does exist, would we be able to feel it? Could you feel it with your own hands?
If we were to feel it with our hands, we could measure it and characterize it. The fact that we cannot measure it basically means that most likely I cannot feel it. So no one has felt it and measured. When we can enhance that feeling and be very, very precise and listen very careful of what's happening, we may find some hints of what it is. We may find it in one or the other way, but we have to be very, very careful and very precise, the nuances. And that's basically the experiments that are being built on the ground, shielded from everything else, and just listen basically to the sound of whether dark matter does something to that we didn't expect without it. And people are doing that very diligently for a long time, ever precise. And currently we just know what it is not. Yeah.
There is a slightly technical question from our online audience, John, asking, is there a reason why JWST is unique for solving a lot of the questions that you have actually raised? For example, using the TRGB measurement where, you talked about the helium flash that's as part of a phase through stellar evolution. But why is JWST unique?
So the method has been used, in particular of the TRGB, so this method of measuring the Hubble constant. The currently available telescope were just only good enough to give a measurement of that tip of the red giant branch, so to find individual stars and measure where's the tip to a certain distance out in our universe. And there's just too few supernovas that went off that leads to a good calibration. And what the JWST does, it has the sensitivity to make that same measurement much further out and into where we have a lot more supernovas already went off that we have in our pockets from the last decades of observations, and where we expect also many more to actually go off and observe. In that sense, it opens up a much broader window in the sky.
Great. Well, I know we still have a lot of questions from the in-person audience, but Simon's not going home until he's answered all your questions. And also, since this is, well, essentially your last week physically at Stanford, right? So we need to take full advantage of his presence. So let's thank Simon again. And before we wrap up, I would like to quickly just introduce a few ways to follow KIPAC. If you have enjoyed this lecture and wanted to also tune in for our future lectures. So let me just quickly start sharing screen. So we actually have a lot of different kinds of social medias, as all the other organizations might do. For example, we have here. Great. Okay, so you can see that we have all these social media platforms. For an online audience, you can actually see the URL which will be dropped into the chat. These are the ways to follow us. We have Facebook, Twitter, and also Instagram. So all kinds of things. And especially if you're interested in hearing the third lecture in this series, I would also recommend that you go onto our outreach page, which is simply also on the social media slide that you have. So on the right, you can see we post all our upcoming lectures. This one that just happened, and also the January 31st, where we will have Professor Bruce McIntosh, who is an exoplanet expert, to talk about how JWST will help us better understand and characterize the atmospheres of all those planets that's orbiting other stars. So it's going to be slightly different from what we have already talked about, but it's also going to be a super exciting topic. And of course, you can also see there that you can simply just join our mailing list, and we send out monthly notifications of what we're up to and what we will be doing next. And we're also very excited to pre-announce that next spring, we will be having another series focusing on dark matter. So there will be 3 lectures focusing on wave-like dark matter, particle-like dark matter, and also dark matter candidates from astrophysical sources. So a lot of those I didn't even know about before coming to KIPAC. So should be really fun. And to wrap up, I would like to bring everyone back again to the screen. Thank you all very much for coming and staying through the entire event. We really, really appreciate your attendance, and also would be super grateful if you could kindly provide us any kind of feedback that you're willing to provide. So we will be sending out a short survey tomorrow, also through Eventbrite, where you could tell us how you liked or not liked this event, how you would like to hear from us, and how we could make this event a better fit for you. So with that, I would like to thank everyone and wish you all a safe and wonderful holiday season. So thank you.